Are you able to see my screen?
It is loading. Okay, now I can see it.
Okay, that's it. Basically, yesterday we talked about some basic terminologies in trees.
Yep.
So we know what is a node. Basically, this is something known as a node. Any, a, because we made this data set, right? So basically, every small entity is a node. What is a root? Root is like, you can say, the topmost node from where all the nodes go down and down. So that you can say a start point of a tree is a root. Like a head in a linked list, a root is similar thing.
Mm-hmm.
We just need the root
Okay.
information to tell the information about the full tree. So that is a root. What are children? So basically every node can have at max two children in a binary tree. So basically this is a node and this is a they are known as the children of that particular node. So children. Basically, they are known as children. And basically, parent, obviously, they have a parent-child relationship. They are parents. Obviously, they could also be children of this, no? Yeah. Parent-child relationship or siblings. Siblings, you can say these are siblings. This, this, all are at the same level because, see, they could have cousins, right? Like, they
Yep.
have at same level. So they are, no, they can be siblings. It's generally not used, but yeah, I'm just telling you. Ancestor, I told you, like ancestor could be the nodes which are above in the hierarchy level. So let's suppose for him, he, this node could be ancestor and this node also could be ancestor. So, yeah, both nodes could be ancestor because they're above in the hierarchy. This also could be ancestor. This
Yep.
is not actually. This is not because that belongs to other family. So you should say in the same level. But this side, because in this side, because these are his ancestors, this should not be treated. So, and descendant, obviously, down nodes. So for suppose for this node, this node, this node, this node, and this node, this node, this node, all are descendants. Descendants
Yeah.
means basically all the down nodes. And leaf nodes is very important thing. Leaf nodes generally used many times. Leaf nodes which have no children. Like at the end, when the our tree supposed to be ends, like here, they are leaf nodes. Let's suppose I draw a tree like this, this. So this is a leaf node because it does not have any children, and this is also a leaf node because it does not have any children. A node which does not have any children is known as a leaf. Leaf is basically at the end of a tree. Okay. So let's try to think how can we build a tree. Okay. Build
Yep.
a tree. Let's try to understand how can we build a tree. See, one way is so in English also what we have done. Oh, we can do write a code like this, write a node and this, and then we uh, keep on writing left, right, and then take this node and give the left, right. This is very hectic process actually. You need to
Yep.
track all this node, which node you are trying to write, this left or right. So what we will do, we will instead of this, we'll use the concept of recursion to make the tree. So what I will do is, see, firstly I will do, I will input the data and I will feed into the root. And then I will say, okay, you want to put the data of the left, put it. So basically I will go and I will solve for the root. Basically I solve for one case, root part. Then I will say, oh, enter the data for left node.
Yep.
So it will enter. So basically, okay, let for the whatever root for the root, for whatever root we have entered. Now we have already taken the input and made a node. Here we made a node for root. Now it's a job of the recursion to do that. So basically, I will be returning type would be a node star only, like a pre-node star. So I will take it
Yep.
and will store in the root left, and then I will again call the build tree function. Build tree, and then just pass the root. Let me just again going to start. Let's say how will we write it? So basically, there is a three node star. I am just calling its node only because it
Mm-hmm.
will be very big. So yeah, let's try to start again. Node star. I'm writing the function build tree. So what will be taking as
Okay.
input? Just a root node, basically where you want to give the node star root. So firstly, let's try to enter the data. So we will just inform the user. Here the this count statement are very cout statement very important because in case of recursion, we don't know where we are, right? So we need to ensure okay, we are at the correct place. So this cout statement helps. So enter data for for node for new node, you can say. Okay, this is this, and then what we'll do, just taking int well, and we will just send this well, and then what we will do, we will create a node out of it. So basically, we will do root is equals to you can say new node, and you can say what root or not root well. Basically, whatever input we have taken from the user data, we will put it here. So basically, we have done the root is equals to new node well, and then this is done. But we are not still. What we have made till now, we'll made like this. This is null, and this is null. Now we need to make it further, right? So what we
Yep.
will do, we will call. We have solved for this part, root part. Now we will call the recursion. Recursion, will say out enter data for left of left node of now which left. It's very important. So I will just make it like this. And whatever data val we have input we have taken, we will call
Okay.
for it. So he will understand, oh, for this you are talking about, oh, one for one you are talking about the left node. So you will call the recursion like this, root dot left, but we need to store also. So basically we will return root dot left, and then we will call the build tree function. It's very smart. Recursion is very smart. So he will do it job root dot. Now similarly you
Yep.
can say okay, no space, just going that. We will just call for right path,
Okay.
enter the data for right node, right of right node you can say, but which node? Uh, again the data node, val node. Just a second. So this is right node, and here we will write node, not node, sorry, val. Whatever val we have taken. Here also it will be val would be one and end of val, and then we will basically root dot right we will call root dot right is equals to build tree, and it will be mm, a root dot. Okay. Now the very important step is left is we have made our tree. Now we have to return the root at the end. Return root, whatever we have made, and then our function is okay. Basically this is our function is in continuation. So it ends here. It is in continuation. So let's try to write this in the code base. We'll understand it better. Okay. Let's try to understand it. It was very important. You'll try to understand deep dive into it because it's a recursion. How it works, you will see that as well. So,
Mm-hmm.
things of here. This payload. Just I changed it actually. Preload is very big. I just said load. Yeah, try to write the main function. Yeah, now let's try to write the built-in logic. So basically, we'll be returning a node star build tree, and we'll just giving be a node star only, node star root. Now we will ask the user, okay, please user, give me a new node data. Uh, enter enter the data for a new node. Okay, then you will give me the data into val, and we will just take the input. And then what we will do, we will create a new node out of it, new node, and we'll just pass the value val. Our one node is created. Now our job is done. Now the job remaining is for the recursion part. So basically, we will again call this enter the data for left of, and then you will tell the val. Right, okay. So now okay, and then this we have to just tell, and then we will call the recursion root dot left is equals to build tree. We just pass the root dot left. Now this thing will return the complete left of whatever root we have created, and then
Yep.
similarly we will call the right thing, the data for right of this node, and we will just say here right build tree, and eventually what remaining is we have created the node, we have called the right and left function, we just need to return it.
Okay. Okay.
Now, very important thing is left. So, how would we just say whether we have to return a null or not? We have to think that also, right? Suppose, like, I want to make a tree like this. Uh, 1, 2, 3, 4, right? But here we are drawing like this, but internally it is like null here, right? We have to define the
Yep.
nulls. So, what we have to do, whenever I put a data as equal to -1. That means I want to put here there are null. Okay, put there are null. Okay, so this is a standard
Yep.
practice. So basically to write a null. So, yeah. So let's say I want to make this tree. Okay, let's try to make it 1, 2, 3, 4. So, so I will say if or you can say val equal to -1. We will say root equals to null. And you can say val equal to minus one, you can return also null directly. So you no need to go further. Because this you can say a base case, right? Because we have reached a base
Yep.
case. Because here our root node ends. So I think this is done. Yeah, let's try to make it. Let's try to create a node star root here. And let's try to call the root equals to build tree. We just pass the root. We are working on now. Yeah. So basically it asks enter the data for the new node. So let's see. Let me just draw the tree here itself. Hopefully, no, it won't work like that. Yeah. Let's say 1, 2, 3. So firstly one is there. So we'll pass one. So yeah, one we pass. Now he's asking me enter the data. Okay, wait just a second. Okay, why is saying again? Let me think. enter the data for left of one, okay, left of one, and enter the data, okay. So basically, let me just remove here. I just changed it to enter the data. Okay, basically, new node left is also new node, right? That's why he's saying that
Yeah.
this log is also print. So yeah, let's try to print. Let's try to write the data for left of it. So once left is two, we should pass two. Hmm. So basically, pass for two. Now he again asks me enter the data for the left of two. Is there anything in the left of two? No. I say no. Nothing is there. So I will pass minus one. Now he's asking me enter the data of right of 2. Is there anything right of 2? No, there is a null. So basically I will say again minus 1. Now he'll ask me enter the data for right of 1. Is there anything right of 1? Yes, it is 3. So we'll pass 3. Enter the data for left of 3. Is there anything left of 3? Yes, there is 4. Enter the data left of 4. No, nothing is there. Enter the
So
data for right of 4. Nothing is there. Enter the data for right of 3. Nothing is there. Null is there. So yeah, our tree ends here. Let's try to write minus one. Yeah. So here the complete tree was made. Our tree looks like this. Okay. Destroy like one, two, three, and then basically three, and then four. Yeah. This is the look like. Now, how would we know that is it look like this? We have made it, but we have to traverse it also, right? So this is very
yeah,
important. Let's try to understand the traversal techniques. So firstly, let's go with I you can go with pre-order and in order also, but let's try to go with level order traversal. Why? Level order traversal will go level wise. So because it helps you to visualize this is the same tree or not. So one, it goes like this. This level first it will print. It will print in the similar way. In order won't go whatever tree you built in that way. It will cover all the nodes, but it won't go sequentially. It will go left, 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 and then right. So it won't be easily visible. Is it the same tree or not? Because see, nodes could be same, but let's say I made a tree like this. Two, three, four, right? This is also a tree, but these and two are different things. They're different trees because the
okay, okay.
connections are different, right? So, so you need to visualize it properly also. So what we will do, we'll go through firstly the level order terms. In level order terms, what you'll do, it will go level wise. Firstly, go this level, then it will cover all the nodes in this level, and this is covered in this level. Okay.
Yeah,
So let's try to understand how we'll go. So we will be using a queue for this. And now why queue and how will it will help? Let's try to understand. So what we will do that we will initialize a queue of what type? We will push these nodes into it. So we will need a node star type of queue. Okay. So basically, we created a queue. It is obviously from the STL library. We have imported it. STL library. Basically, we have imported it. Yeah. And then what we have done. Okay. This we have created now. What we will do, we'll do while not of queue, not empty. So basically, what we will do initially is we will push our root node into the queue. Do not push. I'll push our root node into it and let's try to observe what will happen. See, and then we will run at how much time? We'll run for the queue size times. So to create a next level, so we will create a size is equals to queue dot size we will do. And we will run for loop, you can say, or you can say a while loop also. While size minus minus, we will run a loop. What we will do there? We will, here is our queue. I won't make it this, it's like to look like a stack. I'll make a queue like this. in a horizontal fashion. So basically what we have done initially, we have pushed one into it. Okay, got it. Then what we will do? Now see, whenever and we will run this loop, while loop. There are two loops actually. I just told tell you while we will
Yep.
run the this loop is q dot empty. Whenever my queue does not becomes empty, we'll run at that time. And inside this, I've initialized size. What is this size doing here? This is doing to creating differentiating the level because these are levels, right? Here one, two, three in the same level, four in the same level. So this while this size defines the number of nodes into a particular level. So while size minus one.
Okay.
So there you go. Here you write size minus minus. So let's try to understand both these loops. This is the outer loop. Outer loop. Here a particular level we are traversing. Level we are traversing. Traversing. Okay. Now how does the queue works? So basically we get the front element of the queue. So basically what we will do here, we'll just take out node star. You can say temp, you can use any variable. I generally use temp. Temp is equals to q dot front, front contains a node. Okay, that's great. Now let's try to understand what we will do. Basically one we have. Now we will pop it out. Basically we initially outside this while loop, yeah, outside this while loop, firstly we will push our root node here. Push root node outside this while loop. Okay. Now we will see. Okay. One is there. Now what we will do? We just pop it out. We got temp is equals to one. One is a node. Great. Like I'm just telling it it's not a value, but it's a node.
Yeah. Yeah.
One we got. Now let's try to see whether its left is null or not. Oh, left is not null. Let's try to push it. Basically, what we'll do, we'll just push it to. Okay, that's great. Now we will see the right node as well. Oh, right is also fine. Basically, we will push three. So that's great. Now see, our while loop ends. Basically, what happens is we go into for we have only one node in that level, right? Root node. Then we define int size equals to two dot size. Then only one node was there initially, so there only one node. So size is one. While size minus runs for one time. So basically, this while loop ends, and we again comes to here because
Yep.
obviously queue is not empty. We have two or three in the queue, so queue is not empty. So here it comes again. So what is the size of queue now? Two, two, three. Still here. Okay, that's good. You can say here is a new level. Here is a new level. Okay, now we
Okay.
will go. Now, what is the front node of the queue? Two. Two is the front node. Now, if we will pop it out, so basically, now temp becomes two. Now we will check whether anything left is in of two. No, nothing is there. Anything right of two. No, nothing is there. So we will not push anything. That's great. Now what we will do? We'll go. We'll check. Oh, size. What was the size? Size was two, right? So we have traversed once. Now we will traverse one more time in this while loop. So because three is there. Okay. Now we will check whether left of three exists. Yeah, it exists. We'll push it. Okay, we already popped out 3 because we got the front node is 3. Now temp becomes 3 already. So if I change it, yeah, basically our temp is 3. Now it will check
Yep.
whether anything right of 3 exists. No, nothing exists. It's over. Okay. Now see, our size was 2. We traversed for 2 times. So it's over. It again go back here, comes here again because Q size is not empty because still there is one node, 4 remains here. Okay, that's great. Now we Again check the size. What is the size? Only one node is there. So we'll go run a loop for once. Okay. So while size minus, we got a node 4. Okay, that's great. So we just popped it out for 4. 4 comes here. Anything left of 4? No. Anything right of 4? No. Okay. So this time when we come back here from 4 node, we see, oh, nothing is there. Queue becomes empty. Here, queue becomes empty. That means our loop ends. Our traversal ends. That means
Okay.
we have covered all nodes. So basically, let's try to understand the implementation, and I will try run one more time to get a better understanding. So let's try to write a level order traversal for that. So void level order level order. What we will needing? A node, just a node we are needing. Root. So we will initialize the queue. So before that, let's try to import it. Include queue. Hmm. Okay. And then what we'll do? Level order will do just defining the queue as node star queue. Okay. And then we will push this root into our queue. Basically, this is our starting point. Now we will run a while loop. We will run a while loop till when the queue is not empty. Queue is not empty. Okay, got it. Now this is fine. Now we will loop another while loop, but for what time? So basically we define it in size sz q dot size. So basically this size defines how many nodes are there in our this current level. So will this run while size minus. We can run a for loop as well, but yeah, I just run a while loop. Okay? Yeah. Now we just pop out the front element because we are traversing like this. So just make one more page. So basically we are traversing. Like let's say one, two is there, three is there, four is there. Let's say five is there. Basically we're traversing like this. Firstly one will be printed, then two, three will be printed, then 4 will be printed, and 5 will be printed. Okay. So basically, we are
Yep.
going like this. Complete with this, then this, and then this. Yeah. So basically, these two nodes are in a particular level, these nodes are a particular level, this node is a particular level, this node is a particular level, and this defined by the size. Z defines that. So yeah, if we come back here, we will say node star m is equals to q dot front. So this is done, then we will just pop it out. Okay, now we will check whether temp dot left exists or not. Temp dot left is not equals to null. We will just push it. You dot push temp dot left. Okay. Now
Yeah.
again, first temp. So, and then what we will do? We will check here temp dot right exist or not. We will push temp dot right. Just give me a second. I just come back. Okay. Just a second. Okay. Just one second. I just came go to washroom.
Yeah, sure, sure.
Hello, am I audible?
Yeah.
Hmm. Hmm. Sorry for the interruption.
Yeah. No.
Yeah. So two, three we have done. Yeah. So let me just. So here, time dot left, we check, oh, is it null or not? If it is not null, we just push into left. And if it is right is also not null, we will just push into the right. Now, where exactly where we are accessing our node? Here, we are accessing, we will just print it out. Then,
Okay.
dot data, basically, we just print it out. Now, we need to understand where our level ends. After this while loop, our level ends. So what we will do, we will just print a count of end of it so as to differentiate each level. Either then they will print it in the single line. I don't want to print in a single line. I want to you to visualize properly. That's why whenever level ends, you can write a comment here. Level
Okay. Okay.
ends here. You can say level starts here. New level starts here. Okay. And I think more or less our job is done. Yep. Then let's try to see will it work or not. Yep. Let's try to see. Let's try to call this function level order. We just pass the room. Let's try to see that working or not. Oh, okay, we haven't built the tree again. We have to make it. Okay, let's try to make it a simple tree. Uh, as to visualize it better. So let me just make a simple tree like this. One, and then two, and then three. Okay, it will be
Yeah.
easier. Let's try to visualize it. So what is a new node? One, and then on the left of the one. So basically it is two, and to the left of 2 nothing is there, the right of 2 nothing is there, right of 1 3 is there, left of 2 nothing is there, right of 3 nothing is there. So 1 2 3 printed, right? 1 and then 2 and then 3. Let's try to make it more big. Let's try to make it like this. Let's try to make it 4, and let's try to make it 5 here. Can we do that? We can. So yeah, let me just try to do it one more time, and then we will go to the new tower. So, one left of two is two. Left of two is, I think it's five. So it is five. Then left of five, nothing is there. Right of five, nothing is there. Right of two. Right of two also nothing is there. Right of one,
Okay.
something is there. I think it's three. So it's three. Enter the left or left of three, yeah, something is there. It's four. Uh, left of four, nothing is there. And right of four, nothing is there. And the right of three, nothing is there. Yeah. So basically 1, 2, 3, 5, 4. See, so it's printing like this. 1, 2, 3, 4. This is our tree. This is perfectly fine working. And let's try to go and for the next traversal that is known as let's see let's say go with the pre-order traversal. Pre-order. What's the, what is the main idea here? Just try to remember one thing. It is like root left right. Just keep this thing in mind and you can easily write pre-order of any tree. Let's try to write the pre-order for this thing. Two,
Okay.
three, let's say four here and five here. So what it says is, it says nothing. Firstly, you will print root, when you will print left and when you will print right. But how it works, let's try to. So basically we come here, root left, right means we have to print root. So we printed one. Okay. So what it says, now come to left, we come to left. Okay. Now for this, again it says root left, right. So what that does mean? It is a root. It becomes a root. So we will print two. Now we will reach here because it's left now. So basically we
Yeah.
reach here, left. Now again it becomes a root because root left, right. So here also L, RLN, RLN, not RLN, I should say. I'm defining root as L because they are both same. So L and this L left and this is right. So basically N, L and R. Whenever you come to a new node, you say NLR. Okay. Just try to write this and you will understand. Okay. So basically five. Now we come we come here left, nothing is there. We won't print anything. Basically five already was printed. Okay. Now we came to five back again and we go to right. Nothing is there. We came back and we came back to two. So basically left was already done. So we will go to right. Is something right there? No. Right of no, nothing is there. So we again come back. We come back to here. So we just take a right hand here. Okay, that's fine. Now we came to one. Did we go left to two? Yeah, we already did. We go to right of one. Now let's say to this. We came to three. Now this becomes again a new node, new thing. So we will again apply NLR here. NLR. So basically, does it becomes a root? Yes, it becomes. So basically, we print three. So basically, we now we again comes to left of it. So basically, we will print, and then again it becomes another R. Okay. Basically, we'll print four. So that's how it works. So basically, whenever we comes here, and then we go to left of four, nothing is there. We go to right of four, nothing is there. Come back, and then we check three. Is something right of three exists? No. We come back, and yeah, everything overs. Now, right is also completed, left is also completed. Yeah, everything. Let's try to write the pre-order traversal. How will it look like? See, what we have done. Pre-order. We write the, I think in the last class also we have defined the pre-order. Let me just write it again. Void pre-order node star
Yep.
row. So we'll check if if the root is null, root is equal to null, null. We just return. Okay, and then if it is not, we will just print root. Whatever I was doing, NLR. Because firstly, whenever I am reaching a node, I will print it out. Root.data. And then I am calling left, whatever, pre-order, root.left. And now let's try to understand. When we go to root.left, right, it goes back to
Yep.
here. And again, it do this thing, and then it goes back to here. So when it won't reach pre-order directly. You're getting it right because it's very different. Firstly, what will happen? What we have done here, let's start visualize with the code also. Basically, here was what three, one, two, three, and let's say four is there. So what it is doing? Firstly, it's going to one. It's see root dot data printing, so it will print one. Okay. Now it go to pre-order root dot left. Now the function is called for root dot left. So it is called for this thing. Now this becomes our new root. So basically it comes here, it prints here. Okay, it prints two. Fine. Now fine. Now it again call this root dot left function. Means which left? Two is left. So basically it comes to two and it prints four. That's fine. Now when we reach here, we check
Mm-hmm.
whether now we again call the root left for fourth left, but nothing is there. So we will pass null here. Now it will check. Oh, root becomes null. We will just return. So basically here we will return. Now what we'll do? We just came back, right? And now we came to four. We will check now. Roots right. Is something roots right is there? So it is also null. We will pass. We will pass here null. We will check. Oh, it will come back here. Okay. Now actually
Okay.
what happens is in a stack there is a it becomes a stack. Like firstly, we pushed one, then we pushed two, and then we pushed four. Okay, four traversal is completed. Left, right is completed. So it will be popped out from here. This step I am not making. This computer or compiler only is making internally. Okay, so there's four. We come back. Okay, four is popped out now. How it know? I have to go to two on this stack. Internally it is made. So basically, I need to go to two. Now it will check. Oh, left I already completed. I will go to right. Oh, something is there. No, nothing is there. So basically, I will just complete. Oh, two traversals also completed. Now I will go to one now because now my in stack, what is left? One's left. Okay. Now one is left remaining. I go to right. Oh, three is there. I just popped out one and I just fill it with three.
No, okay.
So this is how it is working. Let's try to see the code. Yes. So this is a slightly difficult thing because this involves recursion. We'll try to write two, three times all the three towers and post order in order. So I think we'll understand it better. It's like for me also, it's very difficult to tell also because it's recursion, right? So you have to visualize it, try to visualize it. You'll write two, three times and you will get it. So pre-order, notes, row. So let's try to check. Firstly, this is our base case. Root is equal to.
Yep.
Try to make it a habit. Whenever you're writing a recursion code, try to define the code into two parts: a base case and this three parts actually. Basically, a base case, a recursion logic, you can say a recurrence relation, or calling the
Yep.
functions. So return, you can say a thing, just return. So basically, here you can say uh, base case. Yeah. Now basically we just printed our logic. So basically we just need to print our data. Route root dot data. So basically root dot data. And now we are not doing in any level order fashion. So basically we'll print everything in a line and then we'll just call preorder root dot left and then we will call preorder to root dot right. Let's try to see how it works. So we just call preorder root we call. So yeah, let's try to see. Okay, we need to give the code as well. So I am defining this tree. Okay, one, two, three, and four. Okay, so yeah, let's try to see. So one, then what is the left of one? Okay, something is there. Yeah, two is there. Left of two there. Yeah, four is there. Uh, left of four, nothing is there. Right of four, nothing is there. Uh, anything right of two? Two right of two. Just check. No, nothing is there. Okay. Anything right of one? Yeah, P is there. Anything left of two? No, nothing is there. Right of three, nothing is there. See, now this is our level order. One, two, three, four. From where it comes? Here it comes one, two, three, four. This is our level order. And this is our pre-order. Let's try to understand how it's working. Basically, what it is doing? Firstly, going to one. Firstly, it goes to one, and then it goes to two, then it goes to four, and then it goes to three. So how it is working? See, if you observe it very carefully, right, we have taken
Yep.
input in pre-order fashion only. You go to code again, and let's try to visualize it. So what we are doing here? Firstly, we are taking a root, basically, or here you can say operating a node. Here you are taking input as a root. Now we are calling root dot left first and then root dot right. So basically, we are taking input in the fashion of pre-order only. So yeah, so it takes the input in pre-order fashion only. So this is how 1, 2, 4, 3. And now, similarly, there is something known as post order. So basically, we can directly write the code for that. Just a small change, nothing big change, but we will. Firstly, let's set for in order and then we'll write post. Now, hard. changes in order.
Yeah, okay,
In
okay.
in order, we just change in order. Now let's try to understand how the call changes. See, in order means so here in order. So remember here left, root, right. So basically you can say L and R now. In pre-order it was NLR. Here it becomes L, then root, then right. So firstly left, then root, and then right. Okay, let's try to see.
Yeah,
So in order, let's try to print it, and then we will check also manually. Root is equal to null. Now, firstly, instead of printing root, we will call the left function in order root dot left. Then we will print the node because this is the root printing part. Then we will call the right function in order root dot right. Let's try to see whether it works or not. It should. Let's try to remove these of both of these and in order root will first. I will making this tree only. 1, 2, 3, and then 4. Let's try to see what is the difference between both of them in order and pre-order. Yeah, let's try to define that thing. So yeah, 1 and left of 1 is 2, left of is 4, nothing is there on left of 4, nothing is there on left or right of 4, nothing is there on right of 2, right of 1 there is 3, there's nothing there, it is minus 1. Now see, here it is changing. Now it's saying 4213. And what is an our pre-order? Pre-order was this. Okay, let's try to think how 4213 comes. Okay, so firstly, what I am seeing, it is saying go to left. So I am here first. Okay, it's saying LNR. LNR means go to left. Okay, firstly go to left. I'm not printing. No printing here. Printing happens on N, not anything else. Okay. Now it becomes another new node. It becomes root. So okay, fine. Then it will say LNR. Okay, I go to left. Okay, fine. Now it say LNR. So I go to left. Nothing is there. I came back. Okay. Now it becomes what? Now it becomes N for him because I already went to left. Basically, we will print 4. Okay. Okay, that's fine. Then what it says? Go to right. If something is there, no. So basically, we just came back to 2. Fine. Now for 2, it also becomes what? N because we already traversed 2, right? So basically, we have to print it. Cool. Now we have to go right. If something exists, no, we came back. So now, when we came back, now it asks 1. Oh, we have already covered the left. That's fine. So basically, it becomes N. So we'll print it out. Now I will go to right. Okay. So basically, we went to right.
yeah,
Now, here we still not print because we again apply LNR. So basically, okay, fine. We apply LNR. Now what we'll do? Oh, we go to left of it. If something exists, no. Okay, we came back. Oh, it becomes N now because it becomes root now. So basically, we just print it out. Now we'll go and check right of 3. Oh, nothing exists. Oh, we just came back. Oh, left also completed, right also completed. We came back. So this is how the traversal happens 4213. You can see here 4213. Let's try to make a big tree to try to understand more better all these traversals and then we will wrap it off. Okay.
yeah,
Okay. Let's try to make a big tree. So this time 1, 2, 3, 4, 5, 6, and 7. Let's try to make this and let's try to understand. Let's try to print it first and then we will see how it works. So let's try to in order only. We are going with in order. Once you understand one thing, right, you will be able to write everything. So yeah, let's try to clear it first. Yeah, let's try to write it. It's a big thing. So let me just see. One, two, three. Okay. Basically there is one and then left of is two. And left of two is I think seven. Yeah. Seven. Seven. Anything left of seven? Nothing is there. Anything right of seven? Nothing is there. Anything right of two? Nothing is there. Anything right of one? Yeah. Something is there. Three, right? Three, then four, five. Okay. Three. Left of three is four. Anything left of four? Left of four, nothing is there. Anything right of four? Nothing is there. Anything right of three? I think yeah. Five is there. Five is there. Enter the data for left of five. I think something is there. Five. Six is there. Six is there. Anything? Oh, nothing is there. Nothing is there. Right of five. Nothing is there. Yeah. So basically, seven to one, four, six, six. And let's try to see our. Yeah, we haven't printed level order, but okay. Let's try to. Okay, we assume this tree is correct. Now let's try to see. This is our in order. Seven to one, one, four, three. Let me just copy this.
Okay.
Let's try to see whether we can write manually or not. This thing. The main
Sure, sure.
aim is that we can write it manually. Let's try to see this. Yeah. So this is 7 to 1. Yeah. How it will go? I came here and just write this thing. It is L and R. Okay. So we go to left. Fine. We go here. We write L and R. Okay. We go to left because still there is left remaining. Okay. We go to left. Is there something? No. Nothing is there. We came back. What we have to remember? Oh, I have already towers left. Now it's time to print. Print 7. 7 is printed. Fine. We came to here. Oh, left you have towers. That's great. So basically you have to print 2. Okay, that's great. So we came back to here.
Okay.
Because nothing is there in right. Nothing is there in right, we came back. So okay. Oh, left you have done. Oh, I just need to print myself because I you becomes the middle thing. So now we came to right. We came to right. We came to right. And then we see here we won't print 3. We will we came to 3. Okay. Now we won't print 3. It's very important step. Again we apply LNR.
Yep.
We go to left. And then we will check. Oh, nothing is there. We came back. And we will print 4. This is very crucial. This is very confusing here. We will not print 3. We will again apply LNR thing. We came to 4. Okay. Now we traverse right also. Nothing is there. So we came back to 3. Okay. Now we already covered left of 3. So we have to print 3. Okay. Then we came to right of 3. Now see, again,
Okay.
we should not print 5. We should again apply LNR. We go to left. Okay, we came to 6. Now we will check left. Oh, nothing is there. We just came back to 6. We'll print 6 because it becomes better. Now we'll check right of 6. Nothing is there. We came back to 5. So basically it's there and then nothing is there. 5. We will have to print 5. And then right of 5, nothing is there. So yeah, this is 7 to 1, 4 to 6. This is very important what I have done today. Let's try to write it yourself. Okay. So today what we have discussed, let me just quickly brief it. So basically we have discussed the basic analogies, building a tree, how we are building a tree. We just taking we write a logic for root node and then calling the recursion. Basically calling the recursion for the rest of our logic because today was a heavy class. So basically we wrote a code for building a tree and then a level order traversal. I told you how we are going level order wise. Here a new level starts and we are doing pushing temp dot left and temp dot right and then a pre-order. basically pre-order traversal. It's very simple. See, code is very simple of Preorder compared to level
Yeah.
order. If you think it's very big also, but if you try to understand it, right, level order is very easy to understand. Okay, we are just starting a new level here. We are just pushing nodes, so it's easier to understand. But this code, it's easy. It's easier to write, but tougher to understand because nothing we wrote. We just wrote root.data, we just call the recursion. Now, how this recursion is working, we have explored it here. So basically, we
No,
just
okay, okay.
complete. So for this tree, try to write this pre-order yourself. Okay, I have wrote it, but maybe you get it, you didn't get it. You try to write it. If you didn't get it, we will try to discuss this in the next class, and we will just take carry over the notes over that. So yeah, mostly today, is there anything, any doubts if you have, yeah, feel free to ask. Nothing big. Yeah, today was heavy class. I think you got a lot of doubts. Maybe we can
Yeah.
resolve it today or in the next class.